start talking about the second. Okay, you may have. It would be unusual, but it's not impossible that you would have heard the word titration someplace else. So my question for you is this. If I hand you a sample of some solution, how do you know what the pH is? You've calculated it, but how can you directly test the pH of a substance? Little strips. Okay, anybody else got another way to do it?
Taste it.
No, we don't taste it. How much? Titration. Okay. Well, we're going to examine. So by the end of today, you're going to know at least 2 distinct ways to test physically the pH of a substance. Okay, so we have these neat substances called acid-base indicators, and acid-base indicators are sensitive to different levels of pH. Great. The reason that they work is because they are themselves a weak acid or a weak base. So if you recall back to Bronsted-Lowry, let's look at an equation real quick here. If I take a Bronsted-Lowry acid or a Bronsted-Lowry base, whatever on the product side here is left over from the acid is called the what? Conjugate base. So I'm going to have a conjugate base, and I'm going to have a conjugate acid. And of course this is related to this. Okay, well, fantastic. You know that. Indicators work because this compound and this compound are 2 different colors. Pretty fancy. So when this thing has yet to give up its proton, it's one color before it's donated its proton. Once it has donated its proton, it's now a different color. Ah, pretty slick. The way we show this is with a generalized equation for indicators. So HIN means an indicator and a hydrogen and a proton. And if you printed these straight from PowerPoint, the arrows should be lined up. If you transform them into some other format, the arrows got all screwed up. Yeah, so the arrows should be there. And what this means is that that indicator is going to break up into a proton that can go on with somebody else, and an anion from the indicator. I find it more comprehensible to look at this in this context, and most indicators are acids. Most of them are actually ionizing. If there is a reason not to do it this way, I don't know it yet. There may be. This is, like I said, this is relatively new material for me. I haven't worked with titrations in a long time, so I will certainly accept that you maybe can't do this, but I think you can. I need to ask a better chemist than myself. So what this is saying is that when we have our indicator solution, in solution, we've already got this equilibrium condition existing. We have some things existing in this state and some things existing in one of these 2 states. Okay? That's what we're saying. Okay, so if we look at our generalized equation for equilibrium with an indicator, if we put an acid into this solution, when we put an acid into this solution, what is an acid going to want to do? Donate or accept protons? It's going to donate protons. So if an acid gives up a proton, which of these compounds, just looking at the indicators, would be willing to accept a proton? This lonely anion will accept the proton. So then with an acid, we're going to create this, and we're going to shift the equilibrium back towards this compound. Does that make sense? Now, if we add a base to this indicator, what does a base like to do? And we're talking here about, yeah, it's going to accept protons. Well, is there a compound here, looking at, again, just the indicators, that is willing to give up protons? Yeah, this guy is willing to give up protons, so we're going to end up creating more of this, and we're going to shift equilibrium in that direction. So if we put an acid into the solution, it's going to turn whatever color this compound is. If we put a base into the solution, it's going to turn whatever color this compound is. It's not hard, and it's not a really complicated concept, but for some reason, when you look at it, I think in the book, it seems kind of overwhelming, or it did for me. So now, in the other class, they had asked, are we going to have to know that an acid will shift it one way and a base will shift it the other? I'm not so concerned with you understanding the mechanics of that. The big concepts that I want you to understand is why indicators change color. That the indicator and its conjugate are different colors, and depending on which way we shift equilibrium, you're going to see one or the other of those colors. So that's really what I want you to know. That they end up forming an ion. Okay, so we have multiple chemicals which act as indicators, and we have a wide variety of them to choose from. And I'm going to show you a graphic that depicts some of the ranges of color over which various indicators work. Okay, so this is a series of indicators. I don't know how many are listed here, and the pH scale is along this side. So what you see is the color which this substance would be at a given pH. Okay, so if we look at the first one, methyl violet. At anything above about 1.5, methyl violet is violet. But if we look at very low pHs, at 0 pH, methyl violet is yellow. At 0.5 pH, methyl violet is a nice green. As we climb up to 1, it's a sort of a bright green blue. Yeah, so if you were going to test a substance and you needed to know if the pH was 7 or 10, could you use methyl violet? No. If you wanted to test a substance and you knew that the pH was somewhere close to 0, and you didn't know if it was 0 or 1 or 1.5, could you use methyl violet? Yeah. There are going to be different indicators that are appropriate for a variety of different ranges of pH. So they all have a different effective range. So here's a question I have for you. Looking at these pretty color bars, if you had a solution and you needed to test the pH and you knew it was somewhere between 6 and 8, and you wanted to get that range, pick an indicator that you could use. Don't yell it out, write it down, and then I'm going to have you compare notes with someone sitting near you. So pick the indicator that you would use. You're testing a substance that has a pH somewhere between 6 and 8, and write that down. And I drew in the lines for 6, 7, and 8. If you're watching this at home, you probably want to pause and answer and then hit restart. We have a pick of bromothymol blue, and bromothymol blue is a really good choice. It's got a distinctly different color at 6 than it does at 6.5, than it does at 7, than it does at 7.5. After 7.5, it's a little bit, it's going to be pretty hard to distinguish. But it's going to do a very good job of telling you when something goes from being an acid to being neutral and shifts up into the base range. So good pick. We might have some other answers. Okay, so phenol red is another choice. Now, where bromothymol blue doesn't have much variation between 7.5 and 8, phenol red doesn't have much variation between 6 and 6.5. Phenol red is great. From 6.5, there's a distinctly different color at 7 and a distinctly different color at 8. So that's going to be better on the higher end of that range. Okay, so litmus is the third one you could choose here. And if you look at litmus, it's got a distinctly different color at 7, or 6, 7, and 8. Now, if you had a substance and you needed to know if it was a very concentrated acid or pretty close to neutral, would litmus help you out? You want to distinguish between a pH of 3 and a pH of 6. No. Litmus is and this is usually the first one people pick. The old-fashioned acids turn litmus red, bases turn litmus blue, period. And there's not a lot of distinction between how low or high the pH is. It's pretty much straight up acid or base. This is the most old-fashioned indicator paper. So we've got all these indicators. We can imagine putting this solution into something. How do we get the paper strips that we're all familiar with using. How does that happen? Actually, all that indicator paper is plain strips of paper that have been soaked in one of these solutions. So we're going to look at a couple of different indicator papers. I've got a whole bunch of indicator papers here. I have put up pictures of two different indicators. I've got this one, which is pictured here, and this shows yellow at 0 and a nice blue at 3. Which indicator do you think this would be? Go ahead and look at that picture and write it down on your paper. So yeah, it's probably methyl blue, because if we look at that range, we've got yellow going up to blue, and they may have used something else to get a little bit more distinction between the 2.5 and the 3, which leads to the next question. How can you get a single piece of pH paper that gives you a range from 0 up to 13 or 14? You soak that paper in multiple indicators. So if you have a paper that is soaked in multiple indicators, some of these indicators, like phenol red, it doesn't react to anything until you hit 6.5 or so. Well, if you want to cover the earlier part of that range, you can use something that stops reacting at 6 and is all one color from there on. So it's this very careful sort of calibration of different indicators. Here's one that is a nice golden at 3 and a green at 5.5. What do you think that is? I would say that that's probably something in the bromophenol blue family, and there may be something else added to it, and there are also, I mean, a guy who does a chem wiki prepared this, so there may also be some slight errors in his ranges. But every indicator has a different range in which it reacts. That's really important to consider, okay? Do you feel pretty clear on that concept? Okay, good. Okay, so using pH paper, no matter how many indicators you soak it in, you are never going to get a pH reading of 2.75. 8.32. Not going to happen. Because it's just not going to give you that specific a number. That's more of a calculated number. There's one way to get that, and that's with a pH meter. How many of you have ever used or seen a pH meter? Pool? You don't do those at the pool?
I don't know.
Okay, so let's draw. Okay, so we've got a couple examples of pH meters here, and they're electric. They also make analog meters that have a dial. What it is, it's two probes attached to a box and a battery. And there's a circuit which sends current out one probe, and that current attempts to come back via the other probe. Why would that indicate anything about the acidity of a solution? It shows how electron-rich it is. It shows how many ions are in that solution. It shows how conductive it is. It's basically a conductivity meter. Now, the thing that I don't know, this is a good question for you guys to investigate. So if we took a solution of sodium chloride, is sodium chloride neutral in solution? Yeah, it is. It's not an acid or a base. It's not donating or accepting protons. It's not increasing hydronium or hydroxide. But is a solution of sodium chloride conductive? Yeah, it's quite conductive. It dissociates into ions. Could you trick a pH meter with that? I don't know. It's a question that I have. So, because if it's just looking at conductivity, if it's not sensitive enough to distinguish between different kinds of ions, I don't know if that would impact its ability to get a reading. But questions that I don't have answers for. Okay, so you remember that for any neutralization equation, if we put an acid and a base together and they neutralize one another, we get what? Water and a salt. And the net ionic equation is just production of water. Hydronium, hydroxide, we get water. Most of the salts are soluble. So what that tells us is if we have a container of an acid, there's a very bad flask of HCl. Okay? And I keep adding, let's say, sodium hydroxide to it. Drop by drop by drop. At the point when I've got equal numbers of moles of sodium hydroxide and HCl, they'll be completely neutralized. It'll just be water and salt. And let's actually draw the chemical equation for that. So that's the double replacement reaction. Water and a salt, water and a salt, water and a salt. So if I put in 1 mole of hydrochloric acid, 1 mole of hydrogen chlorides, how many moles of sodium hydroxide could I neutralize? 1. If I put in 20 moles of hydrochloric acid, how many moles of sodium hydroxide could I neutralize? 20. If I put in 362.5 moles of hydrochloric acid, how many moles of sodium hydroxide could I neutralize? Yeah, you're getting the picture here. Equal numbers of moles. And I know that because I can look at this balanced equation and say for every 1 mole of hydrochloric acid I can neutralize 1 mole of sodium hydroxide. And at the point when they're all neutralized, I have this solution, which is neutral. So whatever the pH of this was, whatever the pH of this was, if I mix together equal parts, I get a neutral solution. Huh, interesting. Okay, so this is the definition for your textbook, that titration is the controlled addition and measurement of the amount of a solution of known concentration required to react completely with a measured amount of a solution of unknown concentration. Woo, it's a lot of words. So is there some tool, the important parts here, the important parts that you need to be aware of? Controlled addition and measurement. So is there any device that you have used in this lab that allows you to very carefully add tiny, tiny, tiny amounts of one liquid to another? Biuret. So we've got those biurets, and they've got that little stopcock on the bottom, and by turning that stopcock, you can add the tiniest little amounts of one solution to another. And in fact, titrations are what biurets are typically used for, and you're going to do a titration on Tuesday. Tuesday you'll do a titration. And we have to be able to measure, and the biurets have those volumetric markings, so we can know exactly how much we've added drop by drop by drop. So just to recap then, if we've got a solution of hydrochloric acid and we add sodium hydroxide to it, there's going to come a point when we have equal numbers of moles of HCl and NaOH where it's neutral. This is perfectly sensible to you people, right? This makes sense? If we've got 1 mole of HCl in this solution, at the point when we add 1 mole of NaOH, it's going to be all canceled out? Okay, good. Now, my next question. How do we know when it's neutral? How do we know when this thing is neutral?
We could use an indicator.
We could use an indicator! Brilliant! We could use an indicator! So we would want an indicator that changed color around where? Round 7. Can you think of any? You already did! You came up with 3 indicators that all changed color right around 7. Guess what? Those are the 3 that we commonly use in titrations of this sort. So, okay, so we take some acid, and I'm going to use acid for an example. You could do this with a base too. Some acid of some unknown concentration, and we add an indicator to it. We go drop by drop by drip by drip with drops of a basic solution of known concentration, and then there comes a point where suddenly, magically, it changes color. And in your slides, they're hard to see on here, but if you can view them online, there are a couple different solutions that are used to indicate neutralization. The point when they neutralize is called the equivalence point, because it means we have chemically equivalent amounts. So that's an important thing to know. We have the same number of moles that will cancel one another out. So it might be 1 to 1, it might be 1 to 2, it might be 2 to 3, but it's the equivalence point. We have the number that basically fulfills the balanced chemical equation. And hey, look at that, a bunch of you picked a winner, bromothymol blue. Bromothymol blue is really common because it changes pH right around 7, so between 6 and 7.5 basically. I think that when they are doing titrations in commercial labs, they probably use more than one indicator to nail it down. So you could actually ask your dad, because I'm pretty sure they do titrations at WTI or at Heritage. Mrs. Haylett worked in a chem lab after college because she has the same degree I do with a minor in chem, and they did titrations. It's how you figure out the pH or the concentration of a solution that you don't have another way to figure out. So you can figure out the concentration of an unknown acid or base solution this way. Okay, so if we are talking about hydrochloric acid and we're talking about sodium hydroxide, they're both strong substances, right? HCl is a strong acid and AOH is a strong base. What's true about strong acids or strong bases? Why are they called strong? Because of the degree of ionization. They either ionize or dissociate completely. So if they completely neutralize one another, we're going to actually get a neutral solution. What if we have a weak acid and a strong base? They won't fully neutralize. So we're not going to get a pH of 7 when we're done. So we can't really titrate with weak acids and bases. Not here. It's sort of outside of what we can do. So if you're using a strong acid and a base, you're going to have to choose different indicators because the pH is not going to end up at 7. And that's really all you need to know, is that titrations with strong acids and bases really yield a neutral solution. And if you're using one that is not strong, you're going to have to select different indicators because it'll have to be closer to, your solution is going to end up closer to the pH of the strong thing. Now, what about if you have two weak? If you have two weak substances, a weak acid and a weak base, we don't even titrate that. It's too unpredictable. The equivalence point can be anywhere all over the map, so we just don't do this, and that's important to know. Okay, you're going to have some math problems to work on tomorrow. So, this is the titration math. You have to know, there are 4 things that you can know in a titration problem. You can know the volume of one solution, you can know the concentration of one solution, you can know the volume of the other solution, and you can know the concentration of the other solution. You're always going to know 3 of those. And we're typically interested in solving for the concentration of one of the solutions. So this is a sample problem out of the book. You've got 27.4 milliliters of 1.54 times 10 to the negative second molar barium hydroxide, and we add it to a 20 milliliter sample of HCl. We don't know the concentration, but we're saying that it's neutralized at that point. What we want to know is the molarity of the HCl. Okay, you ready to do some math? Okay, so 4 steps. The very first thing is writing a balanced neutralization reaction. So let's write the balanced reaction for barium hydroxide and hydrochloric acid. There's our formula equation. Balance it. What do you need? Okay, so this balanced equation is going to guide us the whole way through this. What this is saying is that for every mole of barium hydroxide we put in, we can neutralize 2 moles of HCl. Yeah, so I'll commit that to the video. The states are nice to know, but if you forget these on a test, this is really just the first step in solving a larger problem. I'm not going to fault you for not having the states there. Okay, so that's our first step. We have our balanced equation. Our second step is to figure out how many moles of our known substance we used. This is a factor label. We don't need to use a periodic table to figure out how many moles because we have a concentration and a volume. So we're saying that there is 1.54 times 10 to the negative second moles of barium hydroxide in every 1 liter of this solution, and we know that we have 27.4 milliliters of this solution. Is there a way to, is there a way to get there? So 27.4 milliliters of solution. Okay, so if we stop there, pardon my earlier misstep, we would be in moles per milliliter, and we know how many milliliters we have, 27.4 milliliters. So the answer here would be moles of barium hydroxide, and that's what we want. So now we know the number of moles of our known reagent that we used, we can figure out how many moles of HCl that would neutralize, right? Because we have a balanced chemical equation. So we're going to take this number and put it into a factor label, 4.2196 times 10 to the negative fourth moles barium hydroxide. And every 1 mole of barium hydroxide will neutralize how many moles of HCl? 2. And somebody caught that should be times 10 to the negative fourth. Thank you. Okay, so now we have the number of moles of HCl. Do we have a volume of HCl? We do. So we can now do a factor label that's going to give us the concentration of our HCl. Okay, we're set up now. Milliliters will cancel. We'll end up in moles per liter. Okay, when we complete the math, we end up with 4.2196 times 10 to the negative second molar HCl. Now, you could do that as one giant long factor label problem. It would be really cool, but you might lose your place. So you may want to just keep breaking it up to sort of keep yourself on track. You've got a homework assignment, which is number 23, A, B, and D. This is all in the chapter review. Number 24, or no, I'm sorry, 23 is all parts. 23 is all parts. 24 is A, B, D. 25, 26, and 36. We will grade that on Wednesday, May 28th.